and welcome everyone to this presentation on multimodal photoresponsive planar microwave resonance-based colorimetric analysis of liquid color compound for biomedical application. I will have a short introduction on the microwave spirit ring resonators, then how to enabling them to be sensitive to the visible light illumination, and after that, a multimodal sensor that we propose for color detection in microwave region, and a short conclusion. Microwave ring resonators are a type of sensors that are popular due to their versatility, low profile structure, compatibility with different kind of substrate and different kind of fabrication process. And there are in real world application for these kind of sensors, such as like in biomedical applications such as bacterial growth monitoring, glucose sensing, blood glucose sensing, and industrial kind of applications such as ice accumulation detection and gas sensing. If we want to have a short description on how this kind of sensor works, we can consider a metal surface acting as a ground and a dielectric substrate and the transmission line on top of this. When you apply a signal, that signal will be guided between the ground and the transmission line, and the environment will, and they create an electromagnetic wave in the environment. Now, if you place a metallic ring in a close and decent distance to this transmission line, that electromagnetic wave variation will induce a current on the surface of the ring. And the whole structure can be considered as an analogy as an RLC resonator, which means that in a specific frequency, for this example, there is a point that the resonance occurs, and based on that, based on the properties of the resonant, we can distinguish material. And how is this distinguishing happens? After fabrication, we cannot play with the length of the ring, with the distance of the ring with the transmission. But still, there is something that can be altered, and that is the surrounded media, the permittivity of the surrounded media, or in other words, the dielectric properties. Specifically, if we place a material or we alter the properties of the environment media at this gap of the resonator, this resonant profile will alter. It's either the change in the amplitude or in the frequency or the phase of the signal. So that is how the material characterization and sensing can happen using this type of example of the microwave ring resonator sensor. However, there are a couple of things. Like, one of them is that this type of a structure is not sensitive to the visible light illumination, which can be either a good thing or bad thing. And the other thing is that if we put two different materials with very close dielectric properties, the microwave response will have limitation on distinguishing the material with close permittivity or close dielectric properties. Our group recently published papers on how to enable this structure to be sensitive to the visible light illumination or ultraviolet illumination. And the solution was to use titanium dioxide as a ultraviolet sensitive or optical wavelength sensitive material, and putting in the sensitive part of the ring resonator and make the whole structure to demonstrate sensitivity when you illuminate the structure. In another publication, we used atomic layer deposition to decorate or to coat titanium dioxide with cadmium sulfide to make the structure to be sensitive to the visible light or to the optical wavelengths. There are some issues with those solutions. First of all, there is not always like access to the expensive atomic layer deposition, and like it requires facilitated equipment, and it's expensive, it requires knowledge and experience. And on the other hand, there is no glue or nothing to attach the material on the ring, so it lacks portability. And when you want to use it in a robust, in a harsh environment, you may not have a robust response. So our proposed solution was to, what if we use a commercially available light-sensitive passive component and integrate that to the microwave ring resonator, and can we expect to have or see demonstration of the sensitivity to the visible light variation or illumination. So in order to design a good sensor, first I considered a cuvette, which is normally used for biomedical application, and you can fill it with different kind of liquids. And the characteristic of the cuvette container is that it has two transparent side and two opaque side. Based on the geometry of the cuvette, we designed an SRR that, and this time, instead of using the same substrate to fabricate the rings on it, we used a separate substrate as a floating substrate and put two SRRs coupled with each other and the whole structure coupled to the ring resonator. And therefore, we could finally use more area. We created more area to demonstrate sensitivity to the material inside the cuvette. We finalized the geometry and also did a simulation for electromagnetic wave propagation variation when you add a cuvette in the HFSS simulation environment and add water inside it, and you can see the difference due to the variation in the dielectric properties of the environment. Another set of simulation was done to plot the J-surf or current distribution to hypothetically consider wherever we have maximum current variation, is selected to place the photoresistor on it. And this is the final demonstration or final design that was selected to be fabricated with the spot for placing the photoresistor and the mirror spot in the adjacent ring resonator. The SRR was fabricated on a flexible, thin Rogers, and the photoresistors were soldered in it. And the whole substrate was attached using a tape to the cuvette, to the opaque side of the cuvette, and the photoresistor were bent toward the transparent side of the cuvette. Therefore, after having like a 3D printing holder, we can place the cuvette in a way that the SRRs are going to be excited using the transmission line, and the photoresistors are going to be excited using an LED proportional shining the photoresistors. And this is a picture of showing the experimental setup. And the whole structure was placed in the dark chamber in order to control the amount of light that we want to use to shine the structure. And we placed the LEDs and the cuvette in a distance in order, and the whole structure inside the dark chamber to control the amount of illumination. In the first set of experiments, we filled the cuvette with water and once without water and placed it in next to the transmission line. And the experiment was done once in dark and once when the red LED was on. And using this experiment, and that was the base measurement, we demonstrated that microwave resonance can alter due to the visible light illumination. However, the amount of variation can be seen in the amplitude. And that is because the photoresistor, the commercially available photoresistor, is designed to work or operate in the DC situation, not for high frequency. And if it could have capacitive variation due to the illumination, we could also expect to see frequency variation as well. But what is happening is that the conductivity or resistivity of the photoresistor is changing due to the illumination. So therefore, we more see the impact on the amplitude of the response. The main experiment, we created a stock solution using food coloring, a very small amount of food coloring in water, and using serial dilution, we created different kind of concentration of that food colorant. As you can see, with naked eye, you can observe that there is a difference in the appearance of the material or the liquid inside of the cuvette. In the first experiment, we placed the cuvette one by one in the next to the transmission line in the dark environment. Figure A shows the microwave response when there is no visible light illumination. As you can see, you cannot distinguish between the different kind of materials or liquid that you are applying or introducing to the sensor, because their dielectric properties are very close to each other, and the microwave sensor cannot demonstrate like a distinguishable variation in the resonant profile when you introduce different materials, although you can see that there is differences in the appearance. And the amount of sensitivity that it shows is limited. But in figure B, in the same dark chamber, we turned on a red LED light. And the red light, due to the opaqueness or concentration of the colorant inside the cuvette, the amount of the light can be transmitted through the solution and reach out to the photoresistor will vary due to the concentration. And as you can see the like difference and distinguishable variation in the resonant profile of the microwave response. The full version with more comprehensive analysis with more liquids and a comparison with when we don't have a ring resonator is recently published in TMTT. And as a conclusion, I can say that using this method, we demonstrated microwave ring resonator sensors that are sensitive to the optical illumination, which can be used in either for lab-on-chip and miniaturization concepts, or can be used for direct down conversion from optical to microwave wavelengths with a simultaneous response. I wanted to thank my co-authors and my supervisor, and thank you very much for attending.